Assalamu alaikum. Welcome to lecture number 10 of Digital Signal Processing. In this course, we have learned till lecture number 9, Introduction to DSP, some basic terminologies related to digital signal processing, classifications of signals and systems, some important discrete time system and their manipulation techniques, and then we moved on to the topic analog to digital conversion, and there we looked in detail how we can convert an analog signal into digital one by three stages, that is sampling, quantization and coding. In this week we are going to cover another important topic of digital signal processing, which has its wide application, and the topic is discrete time convolution and discrete time correlation. So the lecture contents for this week are broadly classified into three types or three topics. A first one will be the discrete time convolution. In this topic we are going to learn what the convolution is. I hope you have idea of convolution integral of continuous time signals, but here as far as we are interested in discrete time signals, so we are going to learn discrete time convolution, which is also known as discrete time convolution sum. So in this topic we will first going to learn the basics of convolution, what the convolution is and how we can convolve two signals, what are its output and how this output can help us in various applications. So firstly we will discuss some basic definitions or the scenarios of convolutions. Then we will move towards the mathematical procedure which will be followed to compute convolution. Then we will see some examples also to determine how we can calculate convolution between the two signals. Then we will move towards the discrete time correlation. It's just like we have learned, it's the same strategy we have followed in convolution, same strategy will be followed in correlation. First we will discuss its definition and the theoretical aspects. Then we will move towards the mathematical procedure which will be followed to compute the correlation, and then we will start to learn how we can correlate or how we can find the correlation between the two signals by using some examples. Then also we will see some practical application of these two topics, that is convolution and correlation, and I hope you will enjoy this lecture as it is one of the most important domain of digital signal processing. The third topic is implementation of discrete time systems, or basically we can say that the representation of discrete time systems. There are various procedures to represent discrete time systems. We can represent with the help of difference equations. We can represent them in terms of its response, or either we can represent our discrete time system in terms of its block diagram or graphical representation. So in the third topic we will learn how we can represent our discrete time system graphically with the help of block diagram. So we will going to cover this topic in the live session. So the first two topics will be covered in the recorded lectures, and the third topic, which is not which will not take much time, will inshallah be covered in the live session. So moving on towards the first topic, which is a discrete time convolution. Before going to the convolution topic, we will first learn about the impulse and impulse response. As you all know, we have covered elementary signals in our previous lecture, and in that category we have learned unit impulse signal, which is indicated by sigma of n or delta of n. So here you can see we have a graphical representation in which we have represented a system by capital letter H, and specifically this system is assumed to be LTI system. LTI system are basically linear time invariant system. So we have one LTI system denoted by H, and we have some kind of input represented by x of n, and as we are dealing with discrete time domain, so here we have samples of signal, which is sequence basically. So the sequence is represented by x of n, and it is treated as input to this system H. So when we apply this type of input to our system H, then our system will produce some output corresponding to that input. So we can also say that x of n is the excitation and y of n is the response, or in other words we can say x of n is the input to the system and y of n is the output of the system. So this is the generic representation of any system. If we apply any input to the system, it will produce the corresponding output. Depending upon the characteristics of system, it will produce the output. So speaking about the impulse and impulse response, if we consider this system and we assume that at the input side we are going to apply impulse or delta function. So in that case, if we apply impulse as an input, then the output corresponding to that impulse input will be impulse response. So basically what I am trying to say, the output for a unit impulse input is called the unit impulse response, or simply impulse response. Just look at the figure. We have sigma of n or delta of n as an input, and you know that for sigma of n function at n is equal to 0, we have a magnitude or peak of magnitude equal to 1, and otherwise we have function 0. So if we apply this type of input to a function, to a system, then we will get some output which is denoted by h of n, and h of n can be of any shape, any pattern, or any sequence, depends upon the system characteristics. So coming back to the first equation, there I said h is basically representing a system. So h is basically representing the impulse response of this system, and what this equation is justifying us, that if we know the input and if we know the impulse response, then we can determine the output of the system, and which is the very basic definition of convolution too. Since we are considering discrete time systems, an ideal impulse is easy to simulate on a computer or some other digital device, because it is simply a signal that is 1 at the point n is equal to 0 and 0 everywhere else. So here in the slide we can see that we can represent any signal with the help of impulse signal, and by using the shifting property of impulses, any complicated signal can be decomposed in terms of infinite sum of shifted and scaled impulses. You can see here the mathematical relationship, and also you can see from the plot that if x of k is your complicated signal, so you can just formulate it or synthesize it with the help of delayed and scaled impulse. So we have learned how a signal can be decomposed into group of components called impulses. And what is impulse? And impulse is a signal composed of all zeros except a single non-zero point. So in this way, this impulse decomposition provides us a technique to analyze signals one sample at a time. So the input signal is decomposed into simple additive components. Each of these components is passed through a linear system, and the resulting output components are synthesized, or we can say added. So the signal resulting from this divide and conquer procedure is identical to that obtained by directly passing the original signal through the system. So this is basically what I have explained to you is generally a mathematical operation or manipulation technique in which you have applied shifting and scaling and then added up or synthesized the output, and mathematically we can use the term convolution for this operation. So as we are dealing with discrete time signals, this is convolution sum, but if we are talking about the continuous time signal, it will be termed as convolution integral. If you see the plot, the first plot is for delta function denoted by sigma of n. This function is normalized impulse basically, which means that sample number 0 has a value of 1 and all other samples have a value of 0. So because of this very reason, this delta function is termed as unit impulse function. And the second plot is for impulse response, and as its name suggests, the impulse response is the signal that exists a system when impulse function or unit impulse is applied at the input. So if we are talking about two systems, then two systems are different in that way if they have a different impulse response. If they have the same impulse response, then their characteristics are similar. So just as in case of input and output signal, we normally denote x of n as input and y of n as output. So impulse response is usually denoted by h of n. So the statement that is impulse can be represented as a shifted and scaled delta function can be justified by taking an example. Suppose you have a signal x of n composed of all zeros except sample number 8. and assume that value at sample number 8 as -3. So function is all 0 except sample number 8, which has a value of -3. So this signal is same as the delta function shifted to the right by 8 samples and then multiplied by -3. So mathematically you can write x of n is equal to -3 delta of n minus 8. So this is the mathematical representation of that same signal. So if the input to this system is an impulse, such as you apply input to any system as this function, which is x of n, represented by impulse function delayed and scaled, which is -3 delta of n minus 8. So what will be the system output? So this is where the properties of homogeneity and shift invariance are used, which we have studied in the previous lecture. So scaling and shifting the input results in an identical scaling and shifting of the output. So if delta of n results in h of n, means impulse results in impulse response, then -3 delta n minus 8 results in -3h n minus 8. So in other words, the output is a version of the impulse response that has been shifted and scaled by the same amount as the delta function on the input. So if you know a system impulse response, you will immediately know how it will react to any impulse. Since we get to know that response of the system to an impulse and any signal can be decomposed into impulses, all we need to find the response of the system to any signal is to decompose the signal into impulses, and then what we have to do, just calculate the system outputs for each and every impulse and add that output back together. So this process of decomposition, and after decomposition calculating the output for every impulse and then adding up that output, this process is basically the convolution. So since we are dealing with discrete time domain, this is the discrete time convolution sum. So convolution is such an effective tool that can be utilized to determine LTI system's output from an input and the impulse response knowledge. As you can see from the slide, we have two discrete time signals, x of n and h of n. So we can define the convolution by y of n is equal to x of n convolution with h of n. Or using block diagram, we have input x of n, we have LTI system, and we know the impulse response of that LTI system. So we can easily determine the output of that system by using the convolution technique. Y of n is equal to x of n convolving with h of n. So summarizing our discussion for understanding how system changes an input signal into an output signal. First, the input signal can be decomposed into set of impulses, each of which can be viewed as a scaled and shifted delta function. Then secondly, the output resulting from each impulse is a scaled and shifted version of the impulse response. Thirdly, the overall output signal can be formulated by adding these scaled and shifted impulse responses. Or in other words, we can say that if we know system's impulse response, then we can calculate what the output will be for any input signal. This means we know everything about the system. Whatever the input, we can determine the output if we know the impulse response. So convolution is just a formal mathematical operation. Just as we perform multiplication, addition or integration, it is just a simple mathematical manipulation technique. So as addition takes two number and produce third number, so convolution like similarly like this, the convolution takes two signal and produces the third signal. So this convolution is basically very important in the field of DSP. It's also used in mathematics field where we have to use the probability and statistics. In the field of signal processing, convolution is used to describe the relationship between three signals that are input signal and the impulse response, another signal, and the third one is the output signal. So if you look at the block diagram, we have LTI system, we have input denoted by x of n and output denoted by y of n. So here convolution is used with the linear systems. An input signal enters a linear system with an impulse response h of n, resulting in an output signal of y of n. So in mathematical, if we talk about the mathematical expression, then expression is x of n convolve with h of n to yield y of n. Or in words we can say the input signal convolve with the impulse response to make the output signal. So just as addition is represented by plus sign, multiplication is represented by cross sign, so convolution is represented by steric or simply star. So in various programming languages also we can use this notation if that language allows us, or some languages have some special built-in functions such as MATLAB to perform this convolution. So in this plot we can see convolution is used for low pass filtering as well as high pass filtering. So in this example, input signal is the sum of two components. We have used two components to formulate this input signal, and actually three cycles of sine waves and another function which is a rising ramp is used to formulate these input, and simply we add up these two signals to formulate the input. The first one is the three cycles of sine waves, and it is actually representing a high frequency, and second signal is slowly rising ramp signal, which is actually a low frequency signal. So in figure A you can see that the impulse response for the low pass filter is a smooth arc, resulting in only the slowly changing ramp waveform being passed to the output. Or in the part B you can say it is acting as a high pass filter, so it will only allow the more rapidly changing sinusoids to pass. So the input is same but filter is different, or we can say system is different, or we can say the impulse response of system is different. So we can try to understand this concept in the wake of convolution, that if same signal is applied to system having different impulse response, then we will get some different responses, and you can treat that system as a filter and it has some specific characteristics. So you are just basically convolving the two signals to get the output. So you can imagine how we have used convolution in this example of filtering. So here we have another example in which we have used the same input signal, but the system is changed. It means the impulse response of the system is changed, and if we are going to convolve these two signals, we will obtain the output. And actually the impulse response is actually denoting the filter, which is actually inverting attenuator. And what inverting attenuator does, it actually flips the signal. It means top become bottom and bottom becomes top, just flip the signal, and also reduces its amplitude. That's why it is named as inverting attenuator. So notice the length of these three signals. These all three are the signals: input signal, impulse response, and output signal. The input signal is having 81 samples, and impulse response is composed of 31 samples. So it is just an example. In most practical applications, the input signal can be hundred, thousands, or even millions of sample in length. So but as we are taking as an example, so we just considered our input signal as the sample length with 81 samples, and in practical cases it is a much longer length, and the impulse response practically is usually shorter length, so normally about few hundred points. So but the mathematics behind convolution does not restrict us how long these signals are, but it specifies us the length of the output signal. Whatever the length of the input signal or the impulse response, it will process it, but from the length of input signal and impulse response, we can actually determine the length of output signal. So what will be the criteria? Actually, how we can determine the length of output signal? It is very simple. It is just you have to add the length of the input signal plus the length of the impulse response and subtract 1 from this, which means if you consider capital N as the length of input signal, capital M as the length of impulse response, and then the formula for calculating the length of output signal will be M plus N minus 1 as indicated in the slide. So in this example, you can see the input signal runs from 0 to 80. It means 81 samples. 0 sample is also counted because it is a sample. It occurs at n is equal to 0, but it has some value. So total number of samples will be 81. Impulse response. If you see at the impulse response, sample varies from 0 to 30. So the total number of samples will be 31. So by using the formula M plus N minus 1, which means 81, which is the length of input signal, plus 31, that is length of impulse response, minus 1 becomes 111. So our output signal will be of the length equal to 111 samples, and which is also proved from the plot. We get the samples equal to 111 numbers. So for calculating discrete time convolution, we can either use the mathematical expression as y of n summation x of k into h of n minus k, and k varies from minus infinity to infinity, or either by using the second formula in which x is shifted and impulse response remains the same. So you can see that we have the choice to either shift x of k or h of k, means we have the choice to either shift input function or the impulse response. We will get the same output in both the cases. The convolution operations satisfy a number of useful properties. Some of them are listed on the slideshow. First one is commutative property, and commutative property states that if x of n is a signal and h of n is the impulse response, then either we can convolve x of n with h of n, or either convolve h of n with x of n. We will get the same result. What this expression is telling us, for example, we have a system, we have an LTI system, and its impulse response is h of n, and we will apply input x of n to this system to get the output. So first condition is x of n is our input and the impulse response of that system is h of n. So when we convolve these two signals, we will get the output y of n. So this is the first case. Now consider the second case, which can be treated as if that system response, system impulse response x of n is actually the input signal. What I am trying to say is that if the input we applying to the system is same as the impulse response, which is h of n in the first case, and the impulse response of the system is same as the input in the first case, that is both the input and impulse response are swapped with each other. So in both cases we will get the same output. It means convolution operation is independent, and it is independent of the input and the impulse response. Whatever the input or whatever the impulse response, if we treat the input signal as impulse response and treat impulse response as input, then we will get the same result. But you all know that if we are talking about a system, then it has some fixed impulse response, depends upon its basically parameters on which it is designed. So but this property is telling us we can swap the operation, and after swapping we will get the same result. Moving on towards the second property, which is the associative property, which states that if x of n is a signal and h1 of n is the impulse response of the first system and h2n is the impulse response of the second system, it means two systems are cascaded and x of n is applied at one system and system 1 is cascaded with system 2, and we will get y of n after the system 2, which is the output of cascaded system 1 and system 2 is actually y of n. So this associative property is telling us that x of n convolve with h1 of n first, then convolve with h2 of n, means it is independent of the position of system or the position of blocks in block diagram. Either we apply input to the first system first and then to the second system, or we can apply the input to the second system first and then to the first system. We will get the same output in both cases. I hope you understand this associative property, that convolution operation is independent about the cascaded position of the systems. It will give us the output whatever the cascading position of systems will be, and the output will always be the same whatever the cascading arrangement will be. Now moving towards the third property, which is distributive property, and it states that x of n convolved with h1 of n plus h2 of n will be equal to x of n into convolved with h1 of n plus x of n convolved with h2 of n. It means if we have two systems cascaded with each other, then we can combine their impulse response to get one impulse response, and both the system is grouped together and acted as one system, and that one system, to that one system we can apply input x of n and we will get some output, and this will be the same if we apply input to one system and then get the output, and then we apply the same input to the second system and then we will have some output for that second system too. So if we add these two outputs, we will get the same result as in the first case when we are cascading the impulse response of two systems and then applying the input. So output will be the same in both cases. You can see from the mathematical expression also. In the left hand side, the two impulse response are cascaded or combined and then input is applied or convolved, and on the right hand side, inputs are applied individually to both the system and then added together, and both are equal, we will get the same results. So students, in this lecture we have look into the concept of convolution. We gain the idea what the convolution is, how we can represent our signal with the help of several impulses, what's the impulse response, and how the impulse response is used to perform the convolution operation, because it is just a mathematical operation as we have discussed in this lecture. So I would like you people to search for more examples of this convolution topic. What are the practical applications? Surely we will discuss it in our later lectures also, but I want you people to search for some practical application of convolution in the field of biomedical engineering, how we can use or apply this convolution with some signals related to biomedical. So, and if you have any question or query related to this lecture, you can comment or you may ask it with me in the live session. I hope that you have a basic understanding of this convolution. In the later lecture, we will discuss this convolution with some example in more detail. Then we will see how we can actually calculate the convolution of two signals by taking some examples and some arbitrary signals having some values. So we will look into the procedure or the steps we have to follow to calculate the convolution of two signals. So that's all for this lecture. Thank you.